Dear students, today let us discuss about the VI characteristics of diode, that is voltage current characteristics of diode. Now already we have studied the operation of forward bias condition as well reverse bias condition, and we know more about that. Most commonly used semiconductor materials are silicon and germanium diode. Okay, in the silicon and germanium diode we are going to see the VI characteristics. Now we know that how the conventional current flow. Anode is positive and cathode is negative, and N-type semiconductor as well as P-type semiconductor join together to form a PN junction diode. Now in this graphical representation we can see that y-axis is represented in the terms of current and x-axis in the terms of voltage. Okay, so we represented as I current of milliampere and voltage of forward current as well as reverse voltage. Okay, now we see here, we can see the first quadrant, it has been marked as forward bias. Whenever the voltage increases, the current also increases. Okay, at one point there will be a voltage has breakdown. That means for silicon the maximum cutoff voltage is 0.7 electron volt. For germanium material it is 0.3. So up to this new voltage, after that the current is keep on increasing. Okay, the same way in the reverse characteristics too. In the reverse breakdown voltage, here we can say voltage is minus 50 milliamps for germanium and 20 milliamps for silicon. That is called reverse bias. Okay, so here the reverse breakdown region is in the third quadrant and the forward bias is in the first quadrant. Okay, it's very clear. New voltage is nothing but we will call for germanium 0.3 volt and for silicon 0.7 volt. Okay, so followed by this there are some of the diode parameters. So what are the diode parameters? Forward voltage drop, it is represented by VV. Okay, then maximum forward current, that is IF max. Okay, then reverse saturation current, that is IR. Okay, then reverse breakdown voltage, that is VBR. Okay, then dynamic resistance RD. Okay, these all are the diode parameters. So 5 diode parameters we are going to see. In the VI characteristics we know what is forward voltage, how we are going to calculate maximum forward current as well reverse saturation current as well reverse breakdown voltage. So what do you mean by this dynamic resistance? That is very important. So here you can see the static and dynamic resistance of this diode. Now see, in the y-axis forward current is measured in terms of milliamps, and in the y-axis forward voltage is measured in terms of voltage. Okay, so now if you're considering this forward characteristics alone, so here we are taking the drawing is slope. We are going to calculate the slope, so that in the y-axis we are taking it as change in forward current and the x-axis it is change in forward voltage. Therefore the dynamic resistance RD can be defined by the ratio of change in forward voltage to the ratio of change in forward current. That means the expression can be written as the dynamic resistance RD is equal to delta into VF divided by delta into IF. Therefore, the dynamic resistance can be calculated by RD dash is equal to 26 millivolt divided by forward current. Okay, so this is the thing, and the remaining thing we can calculate everything in the VI characteristics. The next we are going to see about the types of diodes. So types of diodes are classified according to their forward current or reverse voltage. Okay, so here the types of diodes are classified according to their forward current or reverse voltage carrying capacity. Now, here the diodes are classified into three types. One is low current diode, another one is medium current diode, and high current diodes. Okay, low current diodes, medium current diodes, and high current diodes. So, it is nothing but power diodes. High current diodes, we will call it as power diodes. Okay, the forward current capacity for the low current diode is up to 100 milliamps. Okay, and the medium current diode, the forward current capacity is up to 400 milliamps. So the high current diodes will be few amps. The same way for reverse voltage also, low current diode is having the limitation up to 75 volt, and the medium current diode is having the limitation of voltages up to 200 volt. But in the case of high current diodes, there is a several hundred of volt is there. Okay, then followed by this, let us discuss about the diode approximation. So what do you mean by diode approximation? Why we wanted to go for diode approximation? Okay, suppose the any device is need to be replaced by its electrical equivalent circuit. Okay, then we need to work it out the network by traditional circuit analysis. Okay, and we know this once the we use the circuit analysis method, the analysis becomes very simple, and also the time required is very less. Okay, for the analyzation. And also the diode approximation is happened in three ways. The first one is ideal diode approximation, and the second one is second diode approximation, and the third one is linear piecewise approximations, or we can call it as third approximation. Okay, now each model will represent the diode at different level of accuracy. So if we comparing this ideal diode model second approximation, just we are improving the accuracy level of the diode by using one method. The first method what we have used is ideal diode method. Okay, here we are using the circuit that is in forward bias condition, and we have drawn the equivalent circuit. So whenever the forward diode is working in the forward bias condition, the diode will act as a short circuit and you will get the output. Okay, whenever the diode is acting as a reverse bias condition, then it will act as a open bias condition and there will be no output. And this ideal VI characteristics curve shows that the blue line, it has been marked at the origin. Okay, at some point of voltage there will be a cutoff is happening. Okay, at origin itself the current is increasing, as so here it is, we are not at all reaching to the diode maximum level. Okay, now we want to increase this accuracy from the origin to minimum value of the current. So to overcome this disadvantage, we are moving to the second approximation, that is called as practical diode model. Okay, here we have practical diode model. See, whenever the forward bias condition is applied, and also we have applied that bias voltage, right? Bias voltage. Here what is happening? The forward bias characteristics, there is a voltage drop up to 4.7 volt. Okay, there is up to 0.7 volt. Okay, that is called forward voltage. So here, when comparing with the ideal practical diode model, the accuracy of the diode level is increased up to the 0.7 volt. Then followed by the this one, the third model what we are going to see is linear piecewise. It's very clear that while comparing with these two, we are included one dynamic resistance. So what is the use of dynamic resistance? Dynamic resistance is used to do the change of current, ratio of change of current to the ratio of change of voltage. Okay, so in the x-axis it is VF, that is forward voltage, and it is the y-axis, it is the forward current. Okay, whenever the voltage increases, current is keep on increasing. After that, whenever once it reach down to the new voltage, that is points, what is happening? Slope is due to the low forward dynamic resistance. And also here on the reverse bias, there is a small reverse current due to the high reverse resistance. So the complete model in the piecewise is accuracy is verified, and we'll comparing with this ideal model as well the second approximation. The third approximation model gives the good accuracy. Okay. So based on this, let us solve one numerical, that is calculate the forward current for the diode current which is shown in the figure, that is Ri is equal to 10 kilo ohm and Vf is equal to 1.5 volt as well D. Okay, here two conditions we need to calculate this sum. First one we need to calculate at the condition of Vf is equal to 0.7 volt and Rd is equal to 0 ohm. So considering that, we have drawn the equivalent circuit and we are applying the Kirchhoff's voltage law, that is V minus If into R1 minus Vf is equal to 0. Then If into R1 is equal to V minus Vf. Then If is equal to V minus Vf by R1. Substituting the value, we are getting If is equal to 80 milliamps. So what is the second condition here? Here Rd is equal to 0.25. Okay. Then in the place of R1 we should put R1, no, the Kirchhoff's voltage law, how we can write V minus If into R1 minus If into Rd minus Vf is equal to 0. So substituting the values, finally we are getting a If is equal to 78 milliamps. Okay, so today we have discussed about the VI characteristics of diode, then diode approximation methods, and we have solved one problem. Hope everybody understood. Thank